know that if we minimize the C transpose X, this can only get as low as this minus B transpose lambda. And we actually have a little bit more. We have actually strong duality as well, which states that if we have, again, feasible points now X bar for P and lambda bar feasible for the dual problem, and if we have equality in this condition, so C transpose X bar is equal to minus B transpose lambda bar, then this is equivalent to saying that X bar is optimal for the primal problem and lambda bar is optimal for the dual problem, and we actually have KKT conditions with exactly this X bar and the lambda bar. In this case, we don't have a mu because we don't have equality constraints, but you can also show the variant with equality constraints. So this dual problem is important because if we find if we iteratively find better points in the primal problem and then in the dual problem, so that this gap between the two objective values becomes closer and closer to zero, then we can also use this information to find solutions to either problem. All right, and then we went on to discussing how we can actually characterize or find optimal solutions to our minimization problem. And for this, we introduced the notation of vertices and edges. So if we have our feasible set, call this X, which are all X in Rn, such that Ax less or equal B and dx equal to E, then we say that a point V in this set is a vertex of X if we have a rank condition. So if the rank of the matrix A, where we just select the active indices, and the matrix D, which is always active because we have equality constraints, if the rank of this matrix is n, we call this point a vertex. And again, AV is the set of all I in 1 through m, where AI transpose V is equal to BI. Yeah, so this is the somewhat intuitive characterization. If you have a set that looks like this, then you want to call this point a vertex if we have two inequality constraints that meet at this point and that satisfy that the normal vectors are linearly independent. So we don't have two constraints meeting in this way. So it's just a flat continuation, but we really have this vertex here. And this then generalizes with this rank condition to arbitrary dimension. And then we also wanted to say that, well, if we have now vertices, we also want to label edges or properly define edges of our feasible set. And this we also do by a rank condition, but now we want rank n-1. And as we said, we have we call a subset of our feasible set an edge. If we have that the rank of A and D is equal to n-1, where now this active index set of the edge F is just the intersection of all active index sets at all points in our edge. So this A of F is the intersection of all active sets of point X's. Well, these X's are taken from F. And we actually also want that this edge is somehow the full edge and just not a part of it, which also would satisfy this rank condition. So we want that f is the intersection of f of x with this set of active constraints. So with the set of x where ai transpose x is equal to bi for I in these A of F. And this generalizes the notion of an edge also to arbitrary dimension. And now the idea is that we want to devise an algorithm that finds solution to this minimization problem by just checking different vertices and then walking along the edges of this polytope and at some point finding an optimal solution. And for this, we need a result that if we have an optimal solution to this problem, we always have a vertex that's optimal. And this is the following theorem, which states that if the problem minimize C transpose X subject to AX less or equal B and DX equal to E has a solution, then we have a vertex that is minimizes to this problem, or then there exists an optimal vertex. And so this is the idea then of the simplex algorithm later, to just walk along edges of the polytope, so going from one vertex to the next one, by always decreasing this objective value. We also have, so I forgot to mention, we have the vertices and we have the edges, and we say that we have two neighboring vertices if there is an edge that connects them. All right. So far, so good for the recap. And we will have a look at all of these definitions and notations throughout today's exercise. Great. So let's start with the first one, which is, scroll up. Which is this one. So we have seen that if we take the primal problem, so minimize C transpose X such that AX less or equal than B, then we can construct the dual problem. This we have also written in a general way how we can write this. And our first exercise of today is to check out that this is actually we can do this in two ways. So if we take the dual problem and then again the dual problem of this, so this is called then the double dual, then we arrive at our original problem again. So taking this dual problem doesn't only work in one direction, but we can the problems are dual to each other, so to say. And in this context, we also want to exercise again how we can transform minimization problems or maximization problems from one form into the other. So if we have this dual problem, so this maximize B minus B transpose lambda subject to A transpose lambda is minus C, lambda greater or equal to 0, we have this as problem with equality constraints and non-negativity constraints, and we have this general formula for the dual problem of a problem with general inequality constraints. So we first want to rewrite this problem here into a problem with general inequality constraints, then apply that we know how to construct the dual problem of that, and then transform the dual problem of this back to the original problem. So we say that to write this problem star as a minimization problem in, we call this canonical form. We do the following. We replace this equality constraint by two inequality constraints. So we write maximize minus B transpose lambda subject to A transpose lambda is less or equal than minus C, and minus A transpose lambda is less or equal than C. So this, with these two inequalities, we can get the equality case, and we have that minus the identity matrix times lambda. This should be also less or equal than 0. And we can actually, because we want to have a minimization problem, we can rewrite this maximization over minus B as a minimization over plus B transpose lambda. And so we have a problem now in canonical form. So we have minimize some inner product subject to general inequality constraints, and we know that the dual problem of this is the following. We have now maximize the minus this right-hand side vector, so C minus C and 0 times the now variables that are dual to this lambda. And because we have these three groupings into the three blocks of inequality constraints, we also have three groupings of dual variables, and we will call them U, V, and W. And we have the constraint that the matrix here transposed times this new variables U, V, W is equal to minus the objective vector of this original problem. So we have that A minus A and the identity matrix times this U, V, W vector is equal to minus B. And we have that all these now double dual variables should be non-negative. So we have U greater or equal 0, V greater or equal 0, and W greater or equal 0. Okay, and now we see that we have here actually a problem that we saw the last time, how we can get it. So we saw the last time that if we have a general variable with no sign constraints, we can split them up in a positive and a negative part. And we see that the problem that we have here exhibits actually exactly that structure. So we have U and V being non-negative, but we have U entering in a positive way and the V entering in a negative way, but in the more or less same fashion. And also in the objective function, we have U that gets multiplied to C and V that gets multiplied to minus C. So we can group them together and say, okay, let's call X this difference in U minus V. Then we have no sign constraint anymore for X. And then we also see that the last time we saw how we can transform inequality constraints to equality constraints combined with a non-negativity condition by introducing slack variables. And we see that this W is exactly a slack variable. So we add this non-negative W to this AU minus AV, and we get equality. But we see that the W doesn't actually enter in the objective function, so we can just leave it out, and then in the equality condition we can write an inequality condition. So we see that W is a slack variable. And thus we obtain that this problem that we've written down is actually a maximization over sorry, I want to call u x u minus v, but actually the other way around, v minus u, because then our objective function is maximize over minus c transpose x, and we have in the out of this equality constraint, we get a minus ax should be greater or equal than minus b, because we've added this slack variable, or rather, here is a minus missing. That's why this, so we subtract the slack variable, and thus we get equality. And if we don't subtract the slack variable, we have here the left-hand side that's greater or equal than minus b. Sorry. And then we just switch the signs, so this becomes a lesser equal constraint, and we rewrite this maximization over minus c transpose x again as minimization, and so we get that minimize c transpose x subject to ax lesser or equal than b is the double dual of itself, and so we see that taking the dual problem of the dual problem, this brings us back to our original problem. So we see that this relation works in both ways. All right. What we want to do next is also related to this this notion of the dual problem, and for this we introduce a helpful function that's called the Lagrangian. So we again have our standard problem, minimize c transpose x subject to ax less or equal b. And we have this Lagrangian, which is defined as Lagrangian of x and lambda is c transpose x plus lambda transpose ax minus b. So we get the Lagrangian by multiplying the inequality constraint with this new Lagrange multiplier and adding it to the original cost function. This builds our Lagrange functional. And now we want to consider another characterization for optimality. And this is the so-called saddle point condition. So we say that we have a saddle point x bar and lambda bar if we have for any other x's that if we insert x instead of x bar into this Lagrange function, where we still keep the lambda bar, then this makes the object the value of the Lagrange function larger. And if we fix the x bar, then inserting any other lambda, this makes the value of the Lagrangian smaller. So because this reminds us of this function where we have increase in one direction and decrease in the other direction, this is called a saddle point. And our goal is to show that if we have such a saddle point, then this x bar is solution to our minimization problem and vice versa is we have a solution, then the lambda bar, which is the corresponding Lagrange multiplier, together they are a saddle point for the Lagrangian. Okay. So we need to show two directions. So let's first assume that X bar is a solution to this problem. Let's call it again star because it was early also star. Then because KKT conditions hold, yeah, we have seen this earlier. If we have a solution to this problem, then we know that the KKT conditions hold. And we know that there exists an associated Lagrange multiplier lambda bar that's in Rm. And we have the KKT conditions. So as an exercise, let's summarize them up again. We have C plus A transpose lambda bar is equal to 0. So we have no inequality, so no equality constraints. So this is everything that we get from the first condition. We have that AX is less or equal than B. We have that the lambdas are non-negative, and we have the compatibility conditions. So we can only take rows of A that are active in this representation. So the product of lambda bar and AX bar minus B is equal to 0. Again, because of the sign conditions, this equal to 0 condition of the scalar product actually corresponds to a component-wise condition of lambda I bar times A IX minus BI. This is equal to 0 for all I. All right. So our goal is to show that this X bar and the lambda bar is a saddle point for the Lagrangian. So we need to show that these two inequalities hold. So let's first consider a general lambda that's in Rm plus. So any other vector of non-negative entries. And for this, we want to show that L of X bar and this arbitrary lambda, this is less or equal than the Lagrangian evaluated at X bar and lambda bar. So to see this, we first write this expression out. So this is C transposed X bar plus lambda AX bar minus B. And we know that, so this is a transpose, we know that these entries are all greater or equal to 0. And we know that because X bar is feasible, these are all less or equal than 0. So all in all, this inner product is less or equal than 0, and we can just leave it out by taking this less or equal inequality, and we have only C transpose X bar left remaining. But we also see that because we have this compatibility condition that this inner product is equal to 0, we can just add it again to the value that we have. So we know this is the same as C transpose X bar plus lambda bar transpose AX bar minus B. And this then is the Lagrangian at X bar and lambda bar. So we have shown one of the inequality constraints. Again, we have used here that this is equal to 0. Now to show the other direction, so we need that for general X in Rn, we need that for general X, this value becomes larger. Or we will actually show that it stays the same. So if we have a look at L of X bar and lambda bar, We can again write this out. And we can just regroup this, so we can collect all the occurrences of x together and see what's left remaining. So if we do this, we can write this as C transpose plus lambda bar transpose A times x minus lambda bar transpose B. And again, from the KKT conditions, we have seen that this C transpose plus lambda transpose A, which is just this condition, if we transpose it, this factor is equal to 0. This is again equal to 0. And so we can again leave it out, and then we have to have just lambda transpose B. But because this multiplier is equal to 0, we can just add this term again, but now with x bar instead of x here. So this is the same as C transpose plus lambda transpose A x bar. Again, this is 0, but now we have x bar here. And so we can write this again into somehow, sorry, here we had the x bar, and then we got rid of the term, and now we want to have it without the bar, because this is now then the Lagrangian at the arbitrary x, but at lambda bar, this way around. So this concludes that x bar and lambda bar is a saddle point of the Lagrangian. So let's show the opposite direction, so that if we have a saddle point of the Lagrangian, then we know that the x bar solves the optimization problem. So if x bar and lambda bar is a saddle point, so we do a cut here. Now say the other direction, we assume that we have a saddle point. We have by definition that lambda bar is greater or equal than 0. We only consider those lambdas in the definition of the saddle point. So we immediately have this. And now our goal is again to work with the KKT conditions. So to see how we can deduce the KKT conditions from this saddle point property. And then if we have the KKT conditions, we know that the point x bar is optimal. So we have that for all arbitrary x in Rn, that L of x bar lambda bar is less or equal than L of x and lambda bar, which is equivalent to, if we just write it out, C transpose x bar plus lambda bar transpose ax bar minus b. This is less or equal than C transpose x lambda bar transpose ax minus b. And we now want to sort everything to one side. So we say that this is equivalent to, first we have C transpose now x bar minus x, and we have plus lambda bar transpose A x bar minus x, and the lambda bar minus b term, this we have on both sides, so we can just subtract this, and this cancels out. And so we have sorted everything to one side, and we get that this is less or equal than 0. And we can now factor out this x bar minus x term, and then we get that C plus A transpose lambda bar transpose x bar minus x should be less or equal than 0. Now, remember, our goal is to show the KKT conditions, and so the first condition in those is that the C plus A transpose lambda bar is equal to 0. And what we've done now is that we show that for all x in Rn, this inner product of this guy and x bar minus x is less or equal than 0. But because the x is arbitrary, we can take here x bar plus all the unit vectors and minus all the unit vectors. And thus we get that from this less or equal than 0 condition, we actually get equal to 0 condition. So as x in Rn is arbitrary, we get that C plus A transpose lambda bar is equal to 0. Okay, so we now have this condition that's part of the KKT conditions and this one. Now let's see what we can get by using the other property of the saddle point definition. So if we vary the lambdas, so for all lambda in Rm plus, we have now that L x bar evaluated that this arbitrary lambda is less or equal than L and x bar and lambda bar, which again, just using the definition, this is equivalent to C transpose x bar plus lambda transpose AX bar minus B, and this is less or equal than C transpose x bar plus lambda bar transpose AX bar minus B. And we see that we have the same C transpose x bar term on both sides, so we can just cancel this term out. And again, bring everything to one side. And we have here that lambda minus lambda bar transpose AX bar minus B is less or equal than 0. All right. And now again, we want to check what we can do. How can we deduce the KKT conditions from this? So if we set the lambda to lambda bar plus the ith unit vector, which obviously if lambda bar is non-negative and we add the unit vector, this is still something that's non-negative. Then we get out that the AI transpose X minus BI is equal to 0 for all I from 1 through m. And so again, in vectorial notation, we have that AX bar minus B is less or equal than 0, or AX bar is less or equal than B. So we have found another KKT condition, which is just feasibility of X. And what's left is to show the compatibility condition. So if we set lambda to 0, we have that lambda bar transpose AX transpose minus B is less or equal than, sorry, we have minus because we have here a minus lambda bar. This is less or equal than 0.
Here, I have a question.
Yep.
Here, are we constructing now KKT conditions, right?
Yes.
And from there, we can conclude after that X bar is a solution of linear optimization problem, right?
Yes, exactly.
Thank you.
Okay. Yeah, we're actually almost done. So the only condition for the KKT conditions left is the compatibility conditions. And there we have that this product of lambda bar and AX bar minus B is equal to 0. But we actually have this already here because the minus lambda bar, this is something that's less or equal than 0. We also have that this AX bar minus B is something that's less or equal than 0. And because we have this product, we have here a term on the left-hand side that's actually at the same time larger or equal than 0. And because of the condition, it's less or equal than 0. And immediately we get out that lambda bar transpose AX bar minus B is actually equal to 0. And so we have the last KKT conditions. So all in all, so if we take all the conditions that I've marked in red together, we have that X bar and lambda bar satisfy the KKT conditions, and thus we can conclude that X bar is an optimal solution or a solution to the optimization problem. So we've seen now that we can characterize optimality in a bunch of different ways. So we can either describe it with this normal cone condition, or we can describe it with the KKT condition, so some form of an algebraic description. We can use the duality principle, which states that the gap between the optimal values of the primal and the dual problem should be equal to 0. Or we can also equivalently use this the saddle point characterization, which also gives us a condition on the optimality of the point X bar. And we see that more or less all of them boil down to the KKT conditions. So this again highlights how important these conditions are for solving the problem and for coming up with algorithms. All right. With this, we want to leave duality behind us and move on to this notion of vertices and faces and so on. And I've mentioned, or I've written down the theorem that if we have an optimal solution, we can always find this optimal vertex. And now a probably very intuitive idea would be to say, well, then let's just compute all the vertices that we have for our problem and just check all the different optimal values at all these vertices and then find out the one that has the lowest value. And this is something that we want to look at in the next exercise, because the next exercise tells us that we cannot do this, because even though we might have a moderate number of inequality constraints that describe our problem, the number of vertices that we have might grow exponentially in terms of this number of inequality constraints. So even though we might have a moderate number of constraints, we can have a large number of vertices. So it's totally infeasible to calculate just all of them. And this we want to do in the next problem, which is this one. So as a recollection, we have a look at this problem, minimize C transpose X, AX less or equal B. And we have seen that if we have a solution, we we know that it's attained at a vertex, and we want to construct examples here that basically go in two ways. So we want to construct in part A an example of a set that has a moderate number of inequality constraints, but a large number of vertices. So 2 times n inequality constraints and 2 to the power of n vertices. And we also want to show that this also works in both directions. So we can also have sets that have very few vertices, but we actually need a large number of inequality constraints to describe them. So even if we can always find the 2 different descriptions, it's not really feasible in general to switch between them. And the first exercise, or the part A, deals with the hypercube. So in 2 dimensions, it's just the square. In 3 dimensions, it's just the cube, as you all know it. And then this generalizes on. Okay, I think my internet just cut out. Can you hear me again?
Yes.
Okay.
Yes.
Thanks. So we have this generalization of the hypercube, which says that we have in all the coordinate directions 2 constraints. So we have one constraint in the x1 direction, or in both ways, and we have constraints in the x2 direction in both ways, and so on for higher dimensions. And we have that the inner product of x with all of the unit vectors from 1 through n, this is less or equal than 1, and the inner product of the negative unit vectors with x is also less or equal than 1. So if we drew in here a coordinate system, we have here 1, we have here -1, we have here 1, and here also -1. And we want to show that for this set, which has 2n inequality constraints, all of the points x that have coordinates either plus or -1, those are vertices. So we have the point 1, 1, we have the point 1, -1, we have the point -1, -1, and -1, 1. And obviously, because we have n entries in this vector and we have a possibility of either choosing +1 or -1, we have 2 to the power of n different combinations of those. And so if we check that all of those points are vertices, we know that we have this exponential number of vertices. So for part A, we know that first of all, we need to check that those points are feasible, but this is pretty straightforward. So we know that if x is such a +(-1) through +(-1), we have that this ui transpose x is just the ith entry of x, which is again either plus or -1. And we have that minus the ith unit vector times I is -xi, which is then, depending on what you chose earlier, the flipped sign, so either minus or +1. So we know that this is less or equal 1, and this is also 1, so we know that x is feasible. And in order to check whether it's a vertex, we need to check what rank the matrix of active constraints at this point has. So we need to check the rank of A, where we select all the active indices of this point x. Right. And from those conditions, we know that either the constraint with ui, there we have a +1 and we have the equality to the right-hand side. Or if that's not the case, if we have a -1 here, then in the minus ui inequality, we get the plus here, and then we have equality here. So we know that either so for all I between 1 and n, let's write this down. All I in 1 through n, either the ith constraint is active. So if I is in the first 1 through n indices, we have that the positive unit vector constraint is active, or we have that the n plus ith constraint is active. So if the first one are n constraints, then the n plus ith constraint is just minus the ith unit vector. And so all in all, we get that the matrix of the active indices at our point x, there we have all of the different unit vectors. So we have u1 transpose through un transpose. And we have always either plus or minus this unit vector. And what determines whether we have plus or minus is what sign this entry of x has. If x is positive, then ui is active and minus ui is not. And if xi is negative, then minus ui is active and ui is not. So we get that the matrix of the active indices is given just by the sign of the xi's times the ith unit vectors. And because these ui's are all unit vectors, this means that if we take the signs of the unit of the x's and multiplied with the unit vectors as the rows, we just have all of the signs of the xi's on the main diagonal of this matrix. And we have big 0 blocks on the off diagonal. And so we know that the determinant of this matrix is again either plus or minus 1, because on the main diagonal we always have just pluses or minus 1s. And so because this is non-zero, we know that the rank of this matrix is n. So we really have all of these points x that we considered as vertices of the set. And so we have an example where if we increase the dimension, the number of equality constraints increases linearly with the dimension, but the number of vertices increases exponentially with the dimension. Right. And now we want to see whether this again happens only in one direction. So if we have can have a moderate number of constraints, but a large number of vertices. But we see that this also works in the other direction. We can also have examples where we have a large number of vertices and a moderate number of vertices and a large number of constraints, which we want to do in part B. So here we want to have a look at the so-called cross polytope, which in 2 dimensions is just looks the same as a square, but is rotated a little so it sits on its vertex. And in 3D, we have this octahedron that's obtained by somehow gluing up two pyramids together. So in 3D, though, the two sets are actually different from each other. So we have here the octahedron and we have the cube for the two examples. And this is described as the convex hull of all the plus minus the unit vectors. And we actually don't want to show that these are all vertices of the set. We can it's pretty straightforward to show this, but we actually want to find a representation in terms of inequality constraints. And for this, we see that, or as we already saw in the last exercise where we discussed the polarity of sets, that in the hypercube, we had the plus minus the unit vectors as the inequality constraints and the plus minus ones as vertices of the set. And now we switch. Now we have the plus minus unit vectors as the vertices. And we will show that we need all of the plus minus one vectors as the inequality constraints in order to describe this cross polytope. So we set A, matrix A, which is A1 through A to the 2 to the power of n, where AI are all possible vectors from the set plus minus 1 to the power n. And we set B again equal to the constant 1 vector, but now again in R to the power 2 to the power n. And our goal is to show that this, with this choice, we can actually have this. So we define K as the set of all x in Rn, where Ax is less or equal than B. And our goal is now to show that the set C that we defined above and the set K that we just constructed, these are actually the same. Okay, so first let's do one direction. Let's show that C is contained in K. And for this, we know that for every Aj that's in this matrix and Ui unit vector, we have that again, this Aj transpose Ui. This selects the ith entry again from Aj, and again, this is either plus or minus 1, but we know that it's less or equal than 1. And we know that hence all plus minus Uis are in the set K. But because C was defined as the convex hull of all of these plus minus Uis, and we have now that those are all contained in this convex set K, we know that the whole convex hull is also in the convex set K because we can define the convex hull as the intersection of all convex sets that contain these points. So since K is convex, we have that C, which is the convex hull of these plus minus Uis. This is actually contained in the set K. All right, so for the opposite direction, we want to start with some point x that's in K. And we want to show that this is also in C, so we can express it as this convex combination of all of the Uis. So just from this condition, we know that AJ transpose X is less or equal than 1 for J between 1 and 2 to the power of n. And we now want to deduce from this some information about the individual entries of the xi's. And for this, we have a look at the following two conditions added together. So we have the vector containing all ones especially at the ith entry. We know that this times x is less or equal than 1. And we have a look at the vector composed of all minus ones, except for the ith entry where we have a plus 1. Then ith entry. Then we know that the sum of the two conditions is less or equal than 2, but because all of the I ones and minus ones where we stay away from this specific entry, those cancel out. We get here that 2 times xi is less or equal than 2, or xi is less or equal than 1. And in the same way, we get that minus xi is less or equal 1, so xi is greater or equal than minus 1. We also can choose the vector aj, which contains again all of the signs of the entries of x. So we have sine x1 through sine of xn. If we multiply this with the condition, so if we have a look at aj transpose x less or equal than 1, we get that this inner product, we have a sum over the signs of the individual entries multiplied with the corresponding entries. And so because we multiply every entry with its sign, what we have here on the left is actually the sum over the individual absolute values from 1 through n. That this is less or equal than 1. All right. What do these considerations help us now? So we have this condition here, and from those two above, we actually get that again the absolute value of xi is less or equal than 1. And so we can just define these absolute values as some coefficients in a convex combination. So we define lambda I is absolute value of xi for I from 1 through n. And we fix some lambda 0, which is just this 1 minus the sum over the absolute values, which is again, as we just showed, something non-negative. And the absolute values of the xi's are, of course, as well. And all in all, this means that we can express x as the sum from I now being equal to 0 to n. No, it's valued as 1 over lambda I times again a signed unit vector, so sine of xi times ui plus lambda 0 times the 0 vector. And so we have here a convex combination of the set containing the 0 vector and all the sign of xi times ui vectors. But because we know this, we know that this is a subset of the convex hull of 0 and all the plus minus ui's. And we especially know that we have the 0 vector also always as a convex combination of plus and minus any unit vector. So if you take a half plus one unit vector plus a half minus a unit vector, you again get the 0 vector. So this is already in the convex hull of the plus minus ui's. So all in all, this gives that this is contained in the convex hull of just the plus minus ui's because we don't have to additionally add the 0 vector. And we see that this was just the definition of the set C. So we see that we have not directly shown that all these points that we have in this convex hull of this set of points are actually vertices, but you can check that this is true. And so we have constructed these two examples where we have low number of constraints, large number of vertices, and vice versa. And this shows that in general, we can't compute one representation from the other. So that's why we call the representations of these convex sets either H representation, where the H stands for half space or hyperplane or something like this, or we have a V representation, where V stands for vertices, and general we can express polytopes with either one description, but if we have one, it's generally not feasible to calculate the other description from this. And as a conclusion to this exercise, let me paste here the nice image of the 3D sets. So we have on the left-hand side the cross polytope, which if we count all the vertices, we have 1, 2, 3, 4, 5, 6. But if we count the facets, we have 1, 2, 3, 4, 5, 6, 7, 8. So the number of faces is 2 to the power of 3, which is 8. And the number of vertices is 2 times n, which is 2 times 3 is 6. And for the cube, it's the other way around. There we have 8 vertices, but only 6 planes. And we also see that we can observe here this polarity between sets, because all the vertices of this cross polytope, they correspond to normal vectors of the faces of the cube. And the vertices of the cube, they correspond to normal vectors of faces of the cross polytope. So there we have again this two-way connection between the things. Okay, and again, takeaway message is we can't calculate all the vertices in order to find the solution to our minimization problem. Good. Now we've checked this definition of the vertices for this rather abstract example. So in the last exercise of today, we want to have a look at a more specific example, so we can again see what we are actually talking about, how we can imagine this. For this, let's copy over the last exercise. So we have here now a pretty specific example. So we have a bunch of inequality constraints, which are numbered 1 through 7. And we first want to have a feeling of how this polyhedron looks like. First, how we need to choose A and B to describe it. And then we want to determine all the vertices of the set P from the sketch. And then we want to discuss a bunch of related notions. So which vertices are regular or degenerate, and then if we have a edge connecting vertices and so on. So the first thing to do is to actually come up with the matrices in the vector that describe the set. And so we know that we can write this P as all x in Rn, where Ax is less or equal than B. For the choice A, that we get by collecting the left-hand sides of the inequality constraints. So from the x1 plus 2x2, we get a 1, 2, 0 vector. Then we have a 1, 1, 1 vector. Then we have a 3, 0, 1 vector. And then we have a 0, 0, 1 vector. And we've written these non-negativity constraints all together, but again, these are 3 different constraints. And in order to write them as a less or equal, we need to multiply them with a -1. And that's why in this matrix A, we have here additionally -1, 0, 0, 0, -1, 0, and 0, 0, -1. And the matrix B is then just the vector on the right-hand side. So 6, 4, 6, 3, and then 3 zeros for the 3 non-negativity constraints. All right. So I'll try to sketch it by hand, but then I'm also gonna give a nicely plotted picture so we don't have to work with my ugly drawing. First of all, we know that our set is contained in 3 dimensions. So we need a 3-dimensional coordinate system. Not what I want. So let's label this. This is x1, this is x2, this is x3. So first of all, we know that we have the 3 non-negativity constraints. So everything that's feasible is happening in this octant, so to say, that's sitting in front of this coordinate system. So these we don't actually have to additionally draw. And we have here this highlighted in green condition that says that x3 is also bounded from above by a hyperplane that's just orthogonal or parallel to the x1, x2 plane. So we have something like such a hyperplane here that bounds our feasible set, and we take everything that's below. Then we take this 1, 1, 1 condition. There we know that this normal vector just points directly at our face if we draw it like this. And so we get that if the axis goes through the point here, then we know that this is on this hyperplane. Sorry, because we have here a right-hand side 4. This doesn't go through the same point, so we have something like this point, and this point. And this intersects this somewhere here. And then we have the 2 additional constraints. So running out of colors. So this one, this 1, 2, and 0 constraint, this doesn't depend on x3 at all. So it's just a hyperplane that's more or less standing upright on the x1, x2 plane. And this is given somewhere like here. And the last remaining constraint, this 3, 0, 1, this doesn't depend on x2 at all. So this is that comes also straight out of the drawing plane, and it doesn't depend on x2 at all. And if we draw it like this, we get that we have like this. And now we have to collect or to see where those faces intersect. And so we have here this bit of the feasible set, and we have something like here until the red and the yellow, or red and the orange plane intersect, and then we go down to here. We have somewhere that I probably should have drawn this a little bit better. The orange plane, so it goes like this, and so we follow this until here, and then we get back to this. I think the red plane is a little off, and then we have the intersection of the red and the purple one, and something like this. And we have here also this this cutoff that's given by this orange plane. Now let me cheat a little and copy the nice picture over. This is what it should look like if you're able to draw a bit nicer. And we see that we in this I've already labeled all of the vertices. So we have x1 here, which is just the origin of the coordinate system, and then x2, 3, 4, 5, 6, 7, and 8. And now we've determined them in the drawing, but we also need to somehow rigorously define their coordinates. And to do this, the easiest one is x bar 1, which is just the origin. And the constraints that are active here at this point, those are the constraints 5, 6, and 7. Remember, those are just the non-negativity constraints, and at the origin, those 3 are active and all the others are inactive. Then we get that the point x2, this sits in the x1, x3 plane, so the x2 coordinate is equal to 0. So we is this right? 6. Sorry, the x2 and the x3 coordinate are equal to 0, and the x1 coordinate is unequal to 0. And this means that the active index set of this point x2 this keeps the constraints 6 and 7, but then we get that this point is determined by this purple constraint, and the purple constraint was constraint number 3. And to check now what's the x1 value of this vertex, we check at which point does this condition become active. So we have 3 times the x1 coordinate times 0 times 0 times 1 times 0 is equal to 6. And from this we know that x2 has 2 as the first coordinate and then 0, 0. And with this, in this way, we proceed with all the others. So at x3 bar, we have the coordinates 2, 2, 0, and we have an active index set of, we have 1, 2, 3, and 7. So at this point we see, and this doesn't clearly come out from my drawing, but this is happening here. At this point we have that 4 inequality constraints become active. So this one, this one, this one, and the one from below. And this means that we have here more inequalities active than we would actually need to describe a vertex. So remember, vertex means that the rank of the matrix of active constraints is equal to n. So in general, we need only n constraints. But here we actually have more. And this means that this we call a degenerate vertex because we have more constraints active that we would actually need. In the algorithm, these degenerate vertices will become a little problematic because there the description of the normal cone becomes a little bit more complicated. But we'll also see how we can deal with those vertices in the algorithmic sense. And so to conclude the list, we have x4 bar, which is equal to 0, 3, 0. We have x5 bar, which is equal to 0, 3, 1. We have x6 bar, which is equal to 0, 1, 3. We have x7 bar, which is equal to 0, 0, 3. And we have x8 bar, which is equal to 1, 0, 3. And the active index sets are of the fourth one. We have 1, 5, 7. Of the fifth one, we have 1, 2, 5. Of the sixth one, we have 2, 4, 5. Of the seventh one, we have 4, 5, 6. And of the eighth one, we have 2, 3, 4, 6. So again, this eighth vertex there, we have again that 4 hyperplanes meet up. So we again have a degenerate vertex here. Right. So this is what we can determine so far from the picture, that all those are vertices. And we determine their coordinates and their active index sets. Now let's check for a select few of them that those points that we actually selected, those are vertices in the definition that we saw in the lecture. So we know that x bar is a vertex if the rank of the matrix of the active constraints at this point is equal to n. And if we have a look at A with all the active indices at x1, we have A, and we need to select the fifth, the sixth, and the seventh row from this, because those are active. And the fifth and sixth and seventh row of this matrix A, this was just this lower block again, which was minus the identity matrix. And so we have -1, 0, 0, 0, -1, 0, 0, 0, -1. And this, we know this has rank 3 because it's a diagonal matrix and we have non-zero entries on the diagonal. We can also calculate the determinant of this. So we know that x1 is indeed a vertex. Okay. Let's have a look at the one of the degenerate ones. So a x3 bar. There we have to look at A with indices 1, 2, 3, and 7. So we know that we have 1, 2, 0, 1, 1, 1, 3, 0, 1, and 0, 0, -1. So this is why we need this rank condition and can't just say that, well, we want the determinant to be not equal to 0 or the matrix to be invertible, because at these degenerate vertices, we can have rectangular matrices of active constraint vectors. So we really need to formulate this in terms of the rank condition. And if you check the rank of this matrix, we again that this has rank 3. So again, x3 bar is also a vertex. And the last one would be number 6. So I've just picked 3 random ones here, which has active indices 2, 4, and 5. So we need to select the rows 2, 4, and 5 from our matrix. So this one, and this one. And then we get that the matrix that we get here is 1, 1, 1, 0, 0, 1, and -1, 0, 0. And this also has rank 3. And so we know that x6 bar is a vertex. All right, so this is the condition that we need to check whether we have vertices. And the remaining task is to show that the index set 1, 2, this actually determines an edge, and we should mark it in the drawing, and we want to show that the endpoints of f are neighboring vertices. So first of all, what's the meaning of this active index set of the edge f? If this is 2 and 4, we have that f are all the x in our polyhedron, where the what is it? Do I want? I want 1, 2, not 2, 4. 1, 2. And those are all the points where x1 plus 2, x2 is equal to 6, and x1 plus x2 plus x3 is equal to 4. From the drawing, we want to find an edge where the first and the second constraint are always active. And so we know that if we have vertices at the end of this edge, we know that the first and the second entry constraint also have to be active at these vertices. And so we get that the constraints 1 and 2 are active at the 5th vertex, and they are active at the 3rd vertex. So we see that if we either connect those vertices, or if we just draw in this set F that's given by these equality constraints directly into our drawing, we will get that this set here, this is our edge F. So we have that this is the edge connecting x3 bar and x5 bar. And if we check the condition that we stated on what does it mean for vertices to be neighboring, we said that we want the rank of the matrix A of the constraints that are active at both indices, at both vertices, sorry. This should be n minus 1, and the rank of this is the rank of A 1, 2. Those are the only common entries. And this is the rank of the matrix 1, 2, 0, 1, 1, 1. And this matrix has rank 2, which is the same as 3 minus 1. So we get that x3 bar and x5 bar are indeed neighboring vertices as we have defined it in the lecture. So this is an example of why the formal notations and definitions that we've seen in the lecture actually make sense and describe in the geometrically setting exactly the things that we want to describe. All right, and we see that these concepts are then very essential in order to come up with a solution algorithm for these optimization problems. All right. And this is actually everything on today's exercise sheet. So if you have any questions, you can ask them now. Otherwise, I would say we conclude for today and meet each other in 2 weeks again.
No questions.
Okay.
Goodbye.
Goodbye.
Goodbye.